So this lecture is section 2.3 from your textbook. So I call it connected objects, and mainly what we're looking at is we're applying Newton's laws of motion in situations where we have more than one object and they're connected by something. So this could be a truck carrying some trailers, two masses being connected by a rope, or things of that nature. So there are some assumptions we make, because we could have some really complicated math for each of these problems, but what we'll assume is that the mass of the rope or the cable connecting the objects is negligible. This means we don't have to include another mass into our calculation. The other thing we can assume is that the tension in a rope or cable is the same at every point. So a tension is an internal force in a rope, and if we assume that the rope carries its tension equally, then we don't have to do anything else that's more complicated in order to figure out how the tension changes depending on how far it is from the source of the original force. Another thing we can say is that the pulleys are frictionless, so that means that they would just change the direction of the tension force only. So, in a situation with connected objects like this truck with two trailers, what we do is we consider all of the objects to be one mass, and we use that single mass to find the acceleration of the system. So if we have the truck, the trailer A and trailer B in this case, if they have three separate masses, and we know the acceleration of the truck, for example, we add all the masses together, multiply by the acceleration, and then we'll end up with the force. But we also have to break the masses up into individual objects afterwards. So once we know the force of the system, the truck, trailer A and trailer B, if we want to know the force, the internal forces, that would be the force of the truck on trailer A, or the force of trailer A on the truck, or the force of trailer A on trailer B, or the force of trailer B on trailer A. What we need to do is break this up into three different free body diagrams. Now, we've already calculated the acceleration. The acceleration for the truck is the same as the acceleration for the trailer A and trailer B. We can then use that acceleration and the mass of trailer A or trailer B to start determining what the forces are on those objects. I'll give you an example here. This is a sled that's attached to another sled by a rope, and sled 1 is being pulled with a force of 120 newtons to the east. So what would happen in this case? I'll draw the free body diagram. Let me just move it over here. So we have the entire system, the free body diagram of this is, I'm just going to call this S for the sled 1 and 2. This free body diagram includes the force that's on sled 1, which was 120 newtons to the east. This question did say it was frictionless because it's on an icy surface, so assume no friction acts between the sleds. Now the mass of sled 1 and the mass of sled 2 are 12 kilograms and 8.0 kilograms respectively. So the mass of 1,2 is equal to 12 plus 8, 20 kilograms. So the force on 1,2 is 120 newtons. I know the mass, I know the force. The acceleration is equal to F over m. And this would be acceleration of 1,2. This is the force of 1,2 and the mass of 1,2. So this becomes 120 over 20. Gets me to 6.0 meters per second squared. That's my acceleration. Now, another thing to note is that the acceleration of 1, 2 is the same as the acceleration of 1, which is the same as the acceleration of 2. All of these are equal to 6.0 meters per second squared. So when you look back at the lecture slide, it says to calculate the tension in the rope. So I'll just show you that quickly here. Calculate the magnitude of the tension in the rope. So to find the magnitude of the tension in the rope, what we're going to do is now break this up into two separate free body diagrams. This is the free body diagram for the mass 2 or sled 2. This is the free body diagram for mass 1 or sled 1. We know that this is 120 newtons. There is a tension force. It's an internal force up here. But when we look at these individually, it's no longer an internal force. The tension force is the same throughout the rope. So here it's a tension force of M2 pulling back on M1, and here it's a tension force of M1 pulling M2. Now I know my acceleration in this case is 6.0 meters per second squared. That's also my acceleration here. So let's find out what my F net would be in situation 1. So F net 1 equals MA. That's going to be, my M in this case was 12 times 6. That will be 72 newtons. So that is my net force. And because my F net 1 is equal to this 120 newtons, subtract the Ft, I can determine that, I have 48 newtons for my F net. For my my F net is 72. My Ft, that's not 72 here, sorry, I was going to redo that. What would happen is my F net is 72 equals 120 minus Ft. So my Ft is 120 minus 72. So it's the same answer, I was just doing the math incorrectly. Ft is 48 newtons. Now I can test this answer by substituting it in here. You don't have to do this, but if this is the case, my F net for this is equal to Ft. So my F net 2 is equal to Ft. That means that my F net 2 is also equal to M2 times A. So would I have, if I substitute 48 here and I substitute 8 here, will my A be equal to 6? And the answer is yes, because A equals 48 divided by 8. A equals 6 meters per second squared. Now another type of problem you'll see that's a connected object problem would be one where we have two hanging masses. And the way to solve this is actually is very similar to solving things when we're on the same plane. We treat the pulley as just a change in direction. So what we could do is we could just straighten out this system into a line. And what we would see, that Ft that's going up in both cases would actually be an opposing Ft, an internal force, when we treat M1 and M2 as the same, or when we draw the free body diagram for M1 or the free body diagram for M2, you'll find that the Ft's are actually pointing at each other, and they are those internal opposing forces. So here's an example. They kind of show you that straightened out. So we had Fg1, the force of gravity on mass 1, is now pointing to the left. Fg2, the force of gravity on mass 2, is now pointing to the right. As long as they're opposing each other, then we know that we've rewritten this correctly. We've straightened out the problem, and now it's a bit easier to solve. So you can apply Newton's laws to objects as a unit or to each object independently, meaning that we can find the whole mass or the whole acceleration of the system. and the acceleration of the system will be equal to the acceleration of each individual object. Actually, that note is important. It says when you treat the objects as a unit, you can ignore the tension because it's an internal force. However, you must include the tension when you analyze the motion of a single object. That's actually the critical part about these problems. When objects are connected, those internal forces, we look at it as a large system to avoid calculating with the internal forces, and then we introduce the internal forces and our system acceleration to then find out what those internal forces are. So I'll go through an example here on this question. So here we have two masses. One is double the mass of the other. Let's draw a free body diagram of the, or actually let's straighten this out first. So before drawing a free body diagram, I'll redraw this problem. Just a quick sketch. What we're going to do is we have our mass 1. It's connected over this pulley with mass 2, and what I'm going to consider is that this direction here is down. This direction here is also down. Let me just move this thing over so we can see a bit more. So that'll be my situation. I've kind of straightened this whole thing out. And when I draw the free body diagram of this now, I will end up with, I'll draw my my two free body diagrams, and then I'll draw my connected one. So this is my mass 1. It has a force of gravity, an Fg1, going to the left, and it has a tension force, Ft, going to the right. My M2 has an Ft going to the left and has an Fg2 going to the right. As a system together, I have M12 and I have an Fg1 pushing this way and an Fg2 pushing that way. Both are pushing down, but they're opposing each other. Because of the pulley, we're actually changing the direction. So while this is down and this is down, we've changed the direction here so that they oppose each other using the pulley. So the next part of this question, after we considered the free body diagram, is to determine what's the acceleration of the mass. And there's some hints on how to do this. Let's go through this here. So we now have the system as a whole. Let's see what is F net. F net is going to be, I'll take it, the positive will be the larger one, so it'll be Fg2 minus Fg1. That's going to be M2 times A minus M1 times A. And this A is the acceleration of gravity, so I guess I'll change that to G so we don't get confused. This is a 17 kilogram object times 9.8 minus 8.5 times 9.8. I didn't work this calculation out beforehand, so I'll just do it quickly. 17 times 9.8 minus 8.5 times 9.8 will be, I'll keep all of the extra decimal here because we're not in the middle of we're still in the middle of a problem. We're not doing our final reporting. So it's 83.3 newtons. Now that I have that, I can find out what my acceleration is, because my acceleration is F equals ma, or rather, it's A equals F over m. And in this case, my m is my M12. So I'm going to rewrite this as 83.3 over 8.5 plus 17. So that 83.3 divided by 8.5 plus 17 gets me to a value of 3.266, going on forever, 3.3 meters per second squared. So the next part of this says that we have to find the tension in the rope. So in order to find the tension, I now know the mass, or the acceleration of the system. It's still 3.3. That acceleration, let me pull up that acceleration is going to be going in the FG direction. So this will accelerate at 3.3 meters per second squared. And this will also accelerate in this direction at 3.3 meters per second squared. So that tells us that this Ft must be greater than that Fg. But this Fg must be greater than the Ft. So let's go back and try to solve this. We'll look at one of these systems. So we'll look at Fg1. So for Fnet1, the Ft minus the Fg1 will be will give us an Fnet1 in the direction of the acceleration. This, in order to solve this, I need to work with my F equals ma equation. So my mass of the smaller object is 8.5. My acceleration is the 3.2666 repeated. This gives me an Fnet1 of 27.766 newtons. I can then substitute this into this equation here. So my, I'll draw it this way here. This becomes 27.766. We don't need all those decimals, but I'll just write them in. Ft minus m1g. So Ft equals 27.766 plus 8.5 times 9.8. So this value plus 8.5 times 9.8 works out to 11.06 repeated, 111. And a rounding for two significant digits, because the lowest significant digits I have in the question is 2. I get 110 newtons. Now notice I don't put a direction for this force. In some cases, it's okay not to put a direction for forces when we're implying a positive or a negative direction, and it's clear in your solution that you're implying that, and it's consistent. But you will never actually put a direction for this tension force, even though in this question the tension force is going to the right. The reason why we don't put a direction is because tension is always an opposing force. So here we have another tension that would be going to the left. So in order to say that our tension is an internal force, we don't include a direction. Okay, I won't spend too much time on these next ones because the concept is the same. But the other type of connected object problems could be where we're involving gravitational forces and horizontal forces. So here we have a mass pulling down on another mass. So the M2 is pulling down via a pulley on M1. That M2 has a force of gravity affecting it. M1 is being pulled to the right while that force of gravity is acting down because the pulley is changing the direction. So again, we can redraw this so that the free body diagram shows is basically in one dimension. That downward motion of the M2 it can be considered a force to the right on M1. Now I'll let you kind of solve this problem here. One thing to consider is we have the force of gravity affecting M1 and the normal force affecting M1, and in a situation that's not frictionless, and this question is frictionless, which is unfortunate because I can't show it to you then. When we have friction involved, that adds another force to the situation as well as tension. So that makes finding the F net just a little bit more complicated, but the concept is still the same. You treat the whole system together. So you find your free body diagram of mass 1 and 2. All of the external forces on that are considered, and in this case it's just the Fg because the Fg2 because the Fg1 matches the Fn1. And then once we find that, we find our acceleration of the system. That acceleration of the system can then be applied to the free body diagram for just one of those two objects to find out the tension in the rope, which is the next question. So I'll let you try the other questions in this lecture. It's nice to have worked out solutions like this as practice. And tomorrow we will do the last lecture in this unit because we're close to finishing dynamics.